Hi everyone, Tina here, and today I'd like to talk about proof. Specifically in this video, I want to talk about the harder type of proof questions that you might come across if you're doing the higher GCSE maths course. I'd recommend you watch my Proof Essentials video before watching this one if you haven't already. Okay, so let's start. Quite often, harder algebraic proof questions will ask us to work with types of number, so things like even numbers, odd numbers, consecutive numbers, and so on. So we do need to know how to represent these with algebra. Let's say you've got an even number that you want to represent. To do that, you can represent that using 2n. So 2 times any number, any integer n, is always going to be even because 2 times anything is always even. Think about it. 2 times 3, 6, even. 2 times 4, 8, even, and so on. Any number you can think of, if you times it by 2, it will be even. That makes odd numbers slightly easier to represent because for an odd number, we just take that even number and add 1 to it, and that will make it odd. Or if you want, you could take away 1, and either way, you'll still get an odd number. Consecutive means one after the other as you go along in a row of numbers. To represent that with algebra, you can use n and then n plus 1, n plus 2, and so on. If you specifically want to make those consecutive numbers even or odd, then you can do a similar process, but just be careful that for even, so for consecutive even, you want to start with 2n, and then your next one along will actually be 2n plus 2, because you want to skip the odd number next to it and jump up to the next even number. Then it will be 2n plus 4, and so on. Similarly, if you've got consecutive odd, you might want to start with 2n plus 1 and then again skip up to the next odd number, so 2n plus 3, 2n plus 5, and so on. Let's work through some examples. Example 1, prove that the sum of any two consecutive integers is always an odd number. So for this one, we want to start with our two consecutive integers. I would probably just use n and n plus 1. The word sum means we want to add those two together. So stick an add between them and see what you get. And this will give us 2n plus 1. This is an odd number. Remember before when we were saying that we could represent odd numbers as 2n plus 1, etc. It's come out here and 2n plus 1 is odd. So you can just underline that and say something like odd and you're done. Example 2, prove that the sum of any 3 consecutive even integers is always a multiple of 6. There's quite a lot going on here, so I would recommend just breaking it down, make sure you understand each part. So 3 consecutive even integers. So maybe we could use 2n for our first even integer. The next one along would be 2n plus 2. And then the next one along after that, 2n plus 4. Again, we've got that word sum, meaning we want to add them all together. Let's do that. And if we do that, we end up with 6n plus 6. If you want to show that that is a multiple of 6, all you need to do is factor out the 6. So 6 on the outside and then n plus 1 on the inside. When you factor out that 6, it's then common knowledge that that is a multiple of 6, because 6 times anything is a multiple of 6. Third example, prove that the sum of the squares of any two consecutive even numbers is always 4 more than a multiple of 8. Just got to break it down. We've got the sum, the squares of any two consecutive even numbers. So for our two consecutive even numbers, we could use 2n and 2n plus 2. And this time we want to square them. So let's square both. And then the word sum means we want to add as well. Now looking at this, we can now expand these brackets. So 2n squared is going to give us 4n squared when we expand. And then this, be careful, is 2 double brackets. So now we can expand those double brackets doing whatever method you prefer. I personally do FOIL, so 4n squared plus 4n plus 4n plus 4. Tidying this up is going to give us 8n squared plus 8n plus 4. How do we show that this is 4 more than a multiple of 8? Well, you can take the 8 out of the first couple of terms, and that therefore is a multiple of 8, and then you can just stick the 4 on the end. So that shows that you've got your multiple of 8 there. 8 times anything is a multiple of 8 plus 4. Example 4, prove that the difference between the squares of any two consecutive integers is equal to the sum of these integers. We should do the difference between the squares of any two consecutive integers first. So it doesn't specify here that it needs to be even integers or odd integers. So you can just go with maybe n plus 1 and n for your two consecutive integers. Now I've put them in that order because we want to square them and then this time take away. So I'm putting the bigger consecutive integer first, take away the smaller one. As always, expanding and simplifying what we have in front of us is going to give us this. When we tidy this up, we're actually just going to end up with 2n plus 1 because the n squareds go away and the rest is 2n plus 1. So that's that side. That's the difference between the squares of the consecutive integers. Now let's have a look at the other part of the statement, which is saying that we want to show it's equal to the sum of the integers. N plus 1 plus n, the sum of those two integers. Again, if you tidy that up, is just 2n plus 1. So now you've shown that they are equal. To finish off, I thought I'd include an example that did not involve algebra at all. This is because you can really be asked about anything in a proof question, so it's best to keep an open mind. Fifth and final example, no algebra this time, just show that the difference between 10 to the power of 18 and 6 to the power of 21 is a multiple of 2. Starting with 10 to the power of 18, take away 6 to the power of 21 because it says the difference. Then I'm thinking about how to break this down to show that we might be able to pull a 2 out eventually. So to do that, what you can do is you can rewrite 10 to the power of 18 as 10 times 10 to the power of 17, just using your power laws. And similarly, you could pull a 6 out there and say that 6 to the power of 21 is the same as 6 times 6 to the power of 20. Let's put brackets around those and then subtract. Now 10, that's an even number, multiple of 2. So let's write that as 2 times 5 times 10 to the 17. And similarly with 6, you can pull a 2 out. So have it as 2 times 3 times 6 to the power of 20. This is good because now we can just pull out a 2 from everything to show that it's a multiple of 2. So pull a 2 out and then big brackets. We've still got 5 times 10 to the power of 17 there. And we've still got 3 times 6 to the power of 20. That bit inside the bracket looks a bit complicated, but it doesn't matter because we've actually solved the problem. We've shown that it's equal to a multiple of 2 because we've been able to pull that 2 outside the brackets. That's it for now. If you found this video useful, please do remember to like, comment and subscribe to my channel if you haven't already, and do pass this on and share the link with anyone that you think might find it useful. Cheers and see you next time.